Hello, everyone. Welcome you all to one more webinar from our Data Mine webinar series. I'm Igor Cavalcanti. I'm an open pit mining consultant for Data Mine Australia. And in this webinar, I will be leading you through some approaches to update your open pit design according to the latest geotechnical review. So we're going to start having a quick overview regarding Studio P and the other open pit solutions. Then I will show to you guys the objective and the context for this webinar. Thirdly, I will be presenting the base case. Then I will move to the scenarios. So then we actually put some hands-on in the software. So then after, we can jump to the conclusion. It will roughly take half an hour to 40 minutes, these presentations. So questions won't be opened during this presentation, but you guys can contact me or on any of the emails below my photo or any of my colleagues if you are in a different country or region. And if you have any further questions, if you need any further explanations regarding specifically of this webinar, please do not hesitate to contact me and just reach me out by the email. So before we start to work on our scenarios and to study our base case, I'd like to give you some context about Data Mine and our topic. So in this webinar, we will be using the software Studio P, which is one of our tools from our broad range of solutions for open pit. So if you are not familiarized with our range of products for open pit, you can hit out our website to have a deeper look in our products. And you can also go to our YouTube channel to check our tutorials, webinars, and overviews for all of our products for mineral resources. So talking specifically about Studio P. Studio P is a design and mid-short-term scheduling tool. It is suitable for short as well as long-term planning. When it comes to design, Studio P offers all necessary CAD tools for you to design manually. However, Studio P most powerful tool is the Auto Pit design. With this function, we are able to generate a complete pit design within few steps, avoiding all the frustration, all the time consuming, and from the manual design. And we can reduce up to 85% our design time using Studio OP. So if you haven't already, go to our Data Mine YouTube channel, hit this subscribe button, make sure to hit the ring bell as well, so then you can receive the notifications when videos are uploaded. And you can check out our videos and webinars for Studio P as well as for the other solutions. So this is our YouTube channel over here. You can easily go through the videos and the playlists, and you can easily find yourself here and go for the solution that you like most or the solution that you need most. Okay. So moving on to the objectives and the context of this webinar. The aim of this webinar is to update in just a few steps an existing open pit. We're going to explore 4 different scenarios according to possible geotech reviews. These geotech reviews are fictional, so by no means I'm trying to introduce some geotechnical parameters over here. Also, we will explore all the scenarios individually, so you guys can see each approach separately for education proposals. However, I would like to emphasize that our approaches that we're going to study here, all the scenarios can be mixed together, can be used together. Okay? So I would like also to put some context about our topic. Basically, the process of designing a pit is a collaborative effort between the several technical departments within a mining company. Therefore, it is an iterative process, normally resulting in various versions of the design until completed. Once completed, normally the design is submitted to a geotechnical review, and from this point, your design can be approved or not, depending if the design is in conformity with the previous provided geotechnical parameters. So, imagining that your design has been approved, why would I be required to update my design again? Well, there's no simple question for that, but there are several reasons for that, and I could display a list of examples here. So in general terms, we can say that an update is required due to more information acquired about our area or our body. This information can come, for example, because a small portion of a wall has been collapsed. Consequently, the geotechnical team had to reassess the stability of that particular area. So then the parameters of that particular area will be specific, it will be changed. Another example could be a more dense drill campaign done, updating the shape of the ore body and consequently changing the parameters to conform with the new information. And I could go on with this list forever. So with that in mind, we can jump to our base case. So our base case is really simple and straightforward. We'll be dealing with a fictional copper gold mine, which has been addressed through different slope regions as exposed by the figure. So basically, these slope regions are split by south and north. So you can see that they are separated more or less by the southern part of the pit and the southern part of the pit. We have as parameters for slope region 1 a face angle of 65 degrees, a bump width of 17 meters, and a bench height of 10 meters. For slope region 2, we have a face angle of 50 degrees, a bump width of 6.1 meters, and a bench height of 10 meters. So the inputs for this base case are the topography for the area, a block model containing the slope radius coded to it. So as you can see by the figure of the block model here, our block model is already configured, it's coded with both slope regions, being slope region 1 represented by the blue blocks and there's slope region 2 represented by the red blocks. And we also have as inputs the design parameters, which are face angle, bump width, and bench height. So before we start to put some hands on the software and work on the scenarios, I would like to explain a bit about how the auto design projections work. If you are not familiarized with the auto design tool, I would like to emphasize again to go to our YouTube channel. There are several videos and tutorials explaining how the auto design works. So since there's not, it is not in the scope of this presentation, I won't be losing too much time on it. So, but one thing that is important for you guys to know about our topic today is the hierarchy of the projection control sets. The AutoP design tool uses a set of rules which can be interactively modified to trigger an automatic regeneration of the current design. So the projection control values at a point are determined using a hierarchy of control sets for face angles and bump widths. So when calculating the projection values, the order in which the set of controls are searched is firstly rosettes, secondly slope region, or in other words, the slope regions that are coded to a block model, and thirdly, the default parameters. So basically, what I'm saying is that the AutoP design tool, when you are projecting your strings, you firstly honor the rosettes if there are any. Secondly, it will honor the slope region if there is no rosettes. And if there is no slope regions, they use the default parameters set at the beginning of your project. Knowing this, we can jump to our scenario 1. So for scenario 1, I would like us to imagine that the slope region 2 has been changed based on the elevation. I mean, the slope region 2 parameters have been changed. So as you can see in the table, there are different parameters for below the level 80 and for above it. So we can say that the changes were done based on elevation. So below the 80 RL, our initial parameters have been kept. As you can see, a face angle of 50 degrees, a berm width of 6.1 meters, and a bench height of 10 meters. However, for above 80 RL, our geotechnical parameters have changed. So instead of 50, now our face angle is 45. Instead of 6.1, now our berm width is 5 above the 80 RL. So coming to the software now, this on my left side is the test for my AutoP design tool. And here in the screen, I have the projections generated by my AutoP design tool. So again, if you're not familiarized with it, with the task over here, there's many tutorials that I can link to you, so then you can quickly familiarize yourself within here. But basically, in this area here, I can set my ramps, I can play with my design surfaces, I can recalculate as many times as I want my projections, as well as I can play with this conditional and berm tapering and advanced tabs here. So then I can adapt my design as the way I wish. So once said that, let's talk about our scenario 1. This pit here is our base case, and we are inside the AutoP design tool screen, as I said. So on the top of the AutoP design task, I can reach pits here, and I can change between pits. As you can see, I have created 5 different pits, being 1 for the base case and 4 for the other 4 scenarios. At this moment, at this point, all the scenarios, all the pits over here are exactly the same. So then we will do the modifications only in the pits that are named as scenario 1. The modifications for scenario 2, I will do only in the scenario 2 pit, and so on. Okay, so in order to modify our slopes, we gotta swap tasks and jump to our define slopes tasks over here. So if I'm not familiar with how to set up everything for your AutoP design, you can check the tutorials, but basically I can say that the settings are set up under the setup rainbow and the design rainbow, and the workflow basically goes from left to right, and it's very straightforward. You just have to assign a topography, assign a planning model, define benches, define slopes, and then you are able to go to the auto-pit design tool. So let's jump to the define slopes task. So as you can see here, I have the same structure to choose the pit. So I want to modify scenario one. So I'll choose the pit for scenario one here. If I swap between pits here, you can see that face angle and bandwidth are set as the same for every pit. So jumping to our scenario one here, I'll start to look and in our slope. So then we can split our slope region into elevations. So basically, in this uppermost table here, you're gonna set the parameters for the regions. And once you click in the region over here, you are able to go to this lower table that is dealing with rosettes. So for our scenario in this webinar, the XY locations are not relevant for rosettes. They are only relevant when we have multiple rosettes, and we have to interpolate these values from these multiple rosettes. Moreover, over here, the influence of each rosette, if you have many, can be adjusted by assigning it an inverse distance weighting, or IDW power value, which is used in the interpolation as well. So to start to modify our design in scenario one here, I can simply select this add from view here and click. This will add X and Y locations of the point where I clicked in my screen. As I said, these XY locations are not relevant for our scenarios over here. However, the Z elevations are very, very important for scenario one. As I said, as explained by the table in scenario one, below the 80 RL will keep the same parameters from our geotechnical parameters in slope region 2. And from above 80 RL, we're going to use different parameters exposed by the table in the presentation. So starting with some hands-on here, I have to choose my lowest elevation here. Over this control bar here, we can play with our benches. So our benches can be displayed over here. So I can quickly see which is my lowest bench, which is the minus 70 RL. So I type it. And then I want a rosette until the level 80. So this first rosette here is being created to say to the software the parameters that our slope region you have below the 80 RL. Since our first case here, our first scenario here, doesn't have any influence in azimuth, we can set any azimuth that we want. So let's say 360, and I can click add here. Now I will set the geotechnical parameters over here as the same as the geotechnical parameters in the uppermost table, since we are dealing with the rosettes below the 80 RL. So let's put here face angle as 50 and burn width as 6.1. So you can see by the drawing of the rosette that in all azimuths over here, our burn width is 6.1 and our face angle is 50. So you can choose if your rosettes are being influenced from top down or from bottom up. It depends on the user. The difference are main in the direction, so you can choose the direction that you feel most comfortable with. Although I have to say that for some specific cases, you might want to use top down and bottom up, but these cases are not in the scope of this webinar. So I will choose top down in this case for my influence, and I will hit here save and close. I'll get back to my auto design task. I will come over here. Just tick off my design surface and my constraints. Now, before we actually modify our design, I would like to jump into some RL, so then we can check the face angle and the berm width below the 80 RL and above the 80 RL. To do so, I will clip my strings here using the benches, so then we don't see so many strings in our screen. So right now I will choose, let's say, RL 60. I can come here to fit data, choose scenario 1, for instance, and tick on my slope region, so then I can see actually where my slope regions are. Then come to the sheets control bar here, double click the block model file, and then I turn it more opaque, so then I can see it better. Now it's better, okay? So I will come over here and I will query the parameters around this area, so then we can check that they are conforming with our base case. So I will hit here, query line. I will come from here to here, and you can see our horizontal distance at 6.1 as set as our base case over here. If I come to this side here, and I can have 6.1 as well, and so on. Okay, so now I will check the angle. So in order to do so, I will hit 1 here for above. It means that I will display the immediate above strings of my bench. So then I can vary between this toe here and this crest here, my face angle. And voila, I have 50 degrees. I have 50 degrees around here as well. And 50 degrees around here as well. Okay, so let's jump to level 100, which is above level 80. Remembering that at this point, we didn't modify yet our scenario 1. So let's check if our berm width over here is 6.1 and our face angle is 50 as well. So let's see, horizontal distance 6.1, horizontal distance 6.1. I will go one above, gradient 50 degrees, face angle 50 degrees. Cool. So now I'll turn off my block model. I will click my benches and go back to my task. Now, if you guys are able to see it, I will click in recalculate here, and some modifications will be done around here. Sorry, I have to jump again to the design just to check one thing. Oh yeah, one mistake of mine. I didn't set up my elevations above 80. So I can always come back here. I can, as I said before, add from view here because X and Y locations doesn't make any difference. And then now I can set the 80 RL as my minimum Z, and I can check my my highest elevation here. It is 260. Jump into this lower table here. I can use the azimuth as 360. Now I'll be back to my presentation just to check the angle. 45 degrees and berm width of 5 meters. And then I'll click add, and then it's done. Save and close again. I'll click in the auto design task, clicking recalculate, and now all changes were done. So let's jump again to the RL60 to check if the parameters have been kept. So coming over here, I will query parameters again. Horizontal distance 6.1, over here 6.1, over here 6.1. Okay, I'll click on above to check the angle. 50, 50. Now let's go to the RL 100, which is above the RL 80. So now we would expect that all parameters are changed. So let's carry around here. Horizontal distance of 5 meters. Around here, 5 meters. Around here, 5 meters. Let's go to one above to check the face angle. 45, 45, and 45. So very simple, easy, and clean to do it. As you can see, in a few minutes, we were able to set this whole wall here as we wished. So it's very straightforward, it's very simple, and it's very powerful, the use of rosettes. So coming back to our presentation here, now we're going to explore scenario 2. Now for scenario 2, our slope region 1 will be modified. The parameters being modified are being modified based on the azimuth. As you can see here in this table here, what is between azimuth 310 and 20. The face angle has turned from 65 to 60, and the berm width has turned from 17 to 12. And for the rest of the azimuth's range, we're going to keep the same parameter as our base case. So let's go back here to our Studio P. I will save and close my task. Always remember to save your task and or at least save it before closing it. It's important because all the modifications that we are doing here will be saved inside your OP database folder. So then you can easily check all your files over there once they are saved. Okay. So let's get back here to define slopes. I'll select my scenario 2. For this approach based on azimuths, again, I will use rosettes to deal with it. Now I will choose my slope region 1 by click on it in this upper table here. And then I will go to this lower table here to start to type my parameters. So once again, I will add my X and Y locations from view. because they are not important. And since the azimuths you'll be influenced all elevations, I will set my elevations from the very first bench to my highest bench. Okay, so we can now come to this lower table here, and now things become more interesting. So I will get back here to our presentation. As you can see, we have two different sets of geotechnical parameters over here. So the difference of them are based on the azimuths. So we want to create a range of azimuth between 310 and 20 and say to the software that the azimuths that are between this range here have these geotechnical parameters over here. Then I will say to the software that from this range over here, my geotechnical parameters will be these ones here. So going back to the software over here, you can start to set all parameters. I have some notes here to remember my parameters. So let's start with the azimuth 310. I will set my face angle as per the table as 60 degrees and my berm width as 12. I'll click here in add. Now I will use the azimuth 20. I will also set face angle of 60 and a berm width of 12. Now, as you can see, I have the drawing of my rosette already here, but if I pass my cursor over here, I can see that for every azimuth, the berm width is 12 and my face angle is 60, but that's not what we want. So basically, you're gonna have to set a range of azimuths from here to here, so then we can use these values over here. So I will choose firstly the azimuth 21 because this azimuth is 1 after the azimuth 20. So then I will set my face angle as 65 and a berm width as 17. Click add. Now I will choose the azimuth of 309 because I want to modify the range between here and around here. So I will set my face angle to 65 and my berm width to 17 and click add. This is very important, guys. Don't forget to click add. Otherwise, you're gonna spend a long time wondering why it didn't work. So let's save and close. And let's get back to our AutoP design task. So now I will go to scenario 2. I want to modify. Take off my design surface. So as we know, our slope region 1 covers around this area over here. So I'm expecting to have changes and abrupt changes around this area here. So if before we do the recalculation, let's jump to some random RL, let's say 70, and check the azimuth of the regions. One important thing that I would like you to know is that the azimuth has to, if it's in the top-down direction, has to be measured from inside to outside. So, for example, here I will measure from the crisp over here to the toe over here. And in my results here, I will have an azimuth of 324. So this azimuth over here is within the range that you are modifying. So let's check the other one here. It is also 336, is also within our range. let's go to the side over here. So this azimuth here is 18. So it's already outside my range of azimuths. So I'm expecting that the software you do modifications in more or less in this area around here. So if I unclip now, and now I will hit the recalculate button, and you can see that the modifications has been done to that area. I would like for you guys to bear in mind that this bump here is being caused by my constraint over here, as well this bump over here. So this is not the azimuth, okay? So if you jump to RL 60 again, you're gonna check azimuths and parameters. I'll begin in this side here because I know that azimuths go all the way here. So I start from this side and go all the way to this side here, okay? So from here to here, I have an azimuth of 294 with a horizontal distance of 17, which is what I'm expecting since in the range of 20 to 310, the parameters are the same as our base case. So if I go a bit further over here, I have the azimuth 300 and I also have the horizontal distance as 17. I'll click one above here just to quick check the angle. So I have an angle of 65 over here, that angle of 65 over here as well. So if you guys are wondering how I'm measuring everything if I'm not using any of the tools over here, it's because I'm typing the shortcut in the keyboard, okay? So then it's more quicker for us to see. Now I will come one below, zero above again, and then I will check now this area over here. That is the area that I'm expecting changes. So I will check around here. So here I have an azimuth of 337 and a horizontal distance of 12 meters. So in the range of azimuths from 310 to the azimuth 20, we have a face angle of 60 and a horizontal distance or berm width of 12 meters. So it is as expected. Let's check around here. 12 again, around here. Now, one interesting thing. You can see that this is increasing from more or less this point here until it becomes 17 again. Why is that? This is something that I would like to mention to you. If you come to the conditioning tab here, we have our blend distance values control values here. So for our base case here and for our presentation here, I set our blend distance as 0, so then we can see clearly the abrupt changes in the slope regions. So as you can see here by these wedges here and here, this is the range of azimuth that I'm expecting. And since over here when I was squaring the points is where my blend distance start to my slope region start to change, my berm width start to change as well from 12 to 17. Okay, so basically in this tab here we are able to play with the blend distance between regions and rosettes, and this will control the distance over which conditioning between regions is applied, okay? So you can play also with the maximum width change and the maximum slope change here. The maximum width change is nothing more than the maximum berm width change that is permitted over a given distance, and the maximum slope change is used to set a constraint on the amount of a face angle can change over a given period. Okay, so quickly let's change the value here to 10, so then you guys will see that our design will be altered. It has been smoothed. If I click here to 200, for example, to be smoothed again, but not in the way I wish. So let's go back to the blending distance at 0. And now I'm satisfied with my changes here. So now, guys, that's it for rosettes. Now I will jump into our scenario 3. So for scenario 3 over here, the change that we have is in slope region 1, and the change that's occurring is the bench height. So the approach here is slightly different. This means that in our north wall, we're going to have double benches. So basically our bench height will be 20 meters. So let's jump back to the software. So for this case here, I'll save and close my task. And instead of going to the define slopes here, I will come to the setup rainbow and go to define benches. I just want to come here to show you that our benches are defined with heights of 10 meters. So how can we modify that? Should I modify it here? The answer is no. So I'll save and close this task again. And then I will jump to define slopes. I'll select my scenario 3 over here. And then I'll start to play with my global benches. So for this case here, we're gonna use this column here, the catch berm column. This column here will aid us to set our bench height as 20. So basically, it works like this. If I roughly draw to you guys here a berm, a face angle, a berm, face angle, a berm, click, change the background color here so then you guys can see it properly. I can say that this berm here is catch, this berm here, this berm here is a standard berm, this berm here is a catch berm, and this berm here is a standard berm. So if I set a value of 6.1 here, I will have 6.1 of berm width for the standard here, face angle of 50, then a 6.1 berm width for the catch berm here, then a face angle of 50, then a 6.1 berm width for the standard here. However, if I set the value here as 0, what the software will understand. So I will basically copy this drawing here. I will say that this is my standard berm with 6.1 meters, my face angle with 50 degrees. Then this level here is for the catch berm. If I set my catch berm as 0, the software oops, there's no berm here, so let's go up. So then it goes to the next bench, and this would be a standard berm as well with the width of 6.1. So face angle 50, catch berm equals 0, go one above, standard berm again. Okay, so pretty simple. So here, the only modification that we need to do is we have to type for the fall and slope region the same values for catch berm as the values for standard berm. So let's put here 6.1 and 6.1 as well here. And I'll set my value for slope region 1 as 0 for catch berm. Important thing, after you do this, you have to come here in this bench constraints tab. And now I will tell the software that for one standard, I will have one catch. For one standard, I will have one catch. But since it's very time consuming to do it all, I can simply come here. Let's become everything standard again. And then I can say that from bench 260 to minus 70 in every 2 benches, set one bench as catch and clicking update. So then I have catch standard as explained. So let's save and close our tasks. Jump to our AutoP design task again. I'll select my scenario 3. So now we're expecting modifications in this part here, in the north wall. So I'm expecting to see double benches over here. So let's click and recalculate and observe the changes. Well, very quick. So if I rotate the design here and come a bit further here, I can see that our benches are being doubled in every 2 benches. So for you guys to see better, I'll come back to the plan view over here. I'll clip my bench to level, let's say 120. I'll choose none above and none below. These are the strings for level 120. So this level is a standard level. So my berm here is the same, as you can see. It's the same as set. And if I go one above and one, if I go two above, sorry, I can see that for my level 130, I will only have this string here. So let's go to level 130, select none above. And as you can see here, it's double better in this side and having a berm with this amount here where the slope regions are being transitioning. Okay, so very quick, very powerful this approach. You can do it in very small steps. You might be wondering what happened here. This is because some constraints of ours that are set to our design, like this one over here. For example, if I delete it and click recalculate again, you can see that the ramp goes again. Okay, so for scenario 3, that's it. So let's now jump to our last scenario, scenario 4. Let's go back to our presentation over here. So this last scenario here, it's a very common scenario. This scenario, you'll be playing with the slope region 2. And in this scenario, I would like you guys to imagine that the solid which our slope region 2 has been defined has been split in 3 different solids, and each of these 3 different solids will have different parameters. So I will explain to you very quickly and in how you can easily do it inside Studio P and then apply the automatic modifications in your AutoP design. So let's get back to our Studio P software over here. I will save and close my task over here. because I will have to play with the solids from my geotechnical zones. So down here, I will select my project files tab. I will come here for the wireframes. Always go for the wireframe triangles. All of these files over here are inside my project folder, which is over here. So I can simply drag and drop the solids to my screen. So I'll come here to the Sheets toolbar. I'll just right-click wireframes and tell the software to reduce the shininess so then we can see better. So our solids are here. We come to properties and color them differently so then you guys can see it better. Okay. So now we're gonna have to code all the solids to our block model. So very easily you can do it. Firstly, we just have to combine all the solids in the same object. To do so, we can come over here in the Sheets bar and reach out the Data Object Manager. In this wizard here, I can come for the combine objects over here, make sure the wireframe is selected in here, and then I'll select the files that I want to combine. Okay, so it's combined. I'll tick off these guys here, and now I will save as this file here. Let's call it combine geotex. Okay, so come to filter here. You can see that you have three different solids in the same object here. And now we're going to code them to our block model. But firstly, I would like to emphasize one thing. To code it to a block model, you got to go to your project folder and you got to access your wireframe files. So if you're not familiarized with data mine for wireframes, you have two files, being one for the points and other for the triangulations. So I'm gonna need to modify the triangulations files because I have to simply name a column inside my triangulation file with the same name as the column of zones that I have inside my planning model. So after I do it, I have to set a value for my solid, so then I can easily identify it afterwards inside the software. So just an example here, I will delete this one very quickly. To do it, you can simply right click here, insert column. I know that my planning module, the column that deals with the zones is called zone region. So I will name the same. I'll choose numeric and then, okay. So since we have slope region 1 and 2, and now slope region 2 is split in 3 other regions, I'm going to call these 3 other regions as slope regions 2, 3, and 4. So for this first region here, I'll call it S2. And I can fill it all the way down. It's true. So now I simply coded my zone solids. Okay. I did the same for the other solids. As you can see here, 3, 4. And now I'll get back to the software and I can query here. And if I pass my cursor over the zone solids, and if you can see the zone region, once I transition between the solids, this one region number changes over there. Okay, so to do this, I simply clicked Shift plus question mark. Okay, so now I will jump to model. I will go to code. This command here applies a code to X, Y, Z coordinates depending on where the points are constrained by the wireframe. Okay, so here I will choose my block model to be the one to copy the points, and I will choose my combined object for my geotext as my wireframe. I will name my output as block model version 02, let's say. Here in fields, I have to assign each field represent the X, Y, Z locations. And here I will assign the field that I want to code. Important thing, we gotta go to this parameters table here, and we gotta change this all points here. We gotta change this value to 1. It means that it will copy all the points from your block model. If the value is set as 0, the points will be only copied from your object. Okay, so now I can click OK, and the command will be run. So now I have that the WF code command here has been completed. I have a messages here saying that. I can jump back to my folder, date modified, and I can see that a file has been created that named block model version 2. I can hold this file here and drag and drop to my screen. Get back to our plan view over here, and now I will tick off all combined geotech zones. And now you can see that our block model has been changed accordingly to the geotechnical zones. So if I come here to project files again and bring our previous block model, I can jump to it and I can see that it was like this before, and now it is like this. Okay, so once you do it, you have to come here to setup and you have to redefine your planning model. So very quickly, you come here, I will add a link. Since it was created in my folder, my block model is already here in my list. Otherwise, you can hit the 3 dots here and look in your drive. Okay, so let's choose block model 2. And important thing, always remember to assign to your PIT the block model that you want. Okay, save and close, and then we can jump to define slopes. Let's go to scenario 1. If you guys don't see any changes here, simply click in manual and click back in planning model, so it will be updated here. So now we can see that instead of 2, we have 4 regions. Okay, so jumping back to our presentation, our parameters here are 50 degrees for slope region 2 and a berm width of 6.1. For slope region 3, you have 55 degrees of face angle and a berm width of 9.2. And for slope region 4, you have a face angle of 60 and a berm width of 12. Okay, so let's jump back to the software. Now I will set my parameters here. I will use my notes. So region 2 is kept the same. However, for region 3, I have a face angle of 55 and a berm width of 9.2. So for region 4, I have a face angle of 60 and a berm width of 12. Okay, very simple. Now we can save and close our task. Let's jump back to our output design tool, to scenario 4. And now we can see that the changes that we defined in define slopes and in our define planning mode will be applied around this region over here. So I will hit here recalculate, and as you can see, the regions has been modified. You can easily see the difference between the regions by these wedges here. Once again, those wedges are here because I set my condition here as 0, so then we would see it better, the changes during our scenarios. But I can always change it to accommodate my design. Let's say to 100. You see, it's moved a lot. It's not desirable. So I can say that I want to change to 20, for instance, and it's not that smooth again. Okay, so we can play with these controls over here to accommodate your design. So for our scenarios, that's it for today, guys. So to conclude this webinar, I would like just to summarize the approaches that we used in our 4 scenarios. So basically, we use rosettes to approach the changes based on elevations and azimuths. We also use the approach of using double benches. So then you can go to the defined slopes, alter your catch berm, and set it as 0, and then you don't necessarily have to change the bench heights. And the third approach would be, if you receive some zone solids, how to code it to your block model. Okay, so thank you so much, you all, for being with me until here. If you guys want to know more about DataMine, please do not hesitate to hit out our dataminesoftware.com website. And please, if you have any questions, if you need any further explanations regarding the subject or regarding any specific subject, you can contact me by the emails below, as well as you can contact my colleagues using the support and the sales email. All these links I will be sending you in a follow-up email, so there's no need for you guys to note right now, to write down right now, but that's it. If you are not from Australia, I would like you guys to check which would be your nearest country or which would be the nearest office that is dealing with your region. Okay, so thank you so much, and I hope this webinar was a pleasure for you. Thank you, guys.